Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 7 of a unit semiconductors. So let's begin with today's class. In today's class, we are going to discuss about the transistors, and this is the part 2 of the transistor. As you have remembered it, that in the last class we were discussing about the transistors, and let's take a summary of this transistors and we will be with the numericals. Basically, it's a what we have understand that is the three terminal devices, and when I say it's a three terminals, one of them is the base, another is the emitter, and one more, it's a collector. So it's a three terminal device. Base, if I see according to the size and if I see according to the doping, so base is least in the size, emitter it's a moderate in size, and the collector is the maximum, or we can say highest in the size according to the doping level. That collector is moderately topped, emitter it is maximum topped, and base again it's a least topped. When we say transistor, then can work transistor can work for three tasks. One of them, it's an amplifier, another, I should say, switch, and within this as a switch, it can work in two parts. It's a on switch or in off switch. When transistor works for amplifier, it works in the active region. And when I say it's an active region, that means its input junction is the forward bias and its output junction is the reverse bias. When I say the transistor works as the switch, and within the switch it can work as a on switch, then its input junction is the forward bias, it's an output junction, it's a forward bias, and this is what we call as a saturation region. It is at saturation region. When I say it's an off switch, its output junction, it is at reverse bias, its input junction, it is at reverse bias, and it works in cutoff region. Yes. Then we have discussed the three uh, modes of configuration. And when we say it's a modes of configuration, one of them is the CB, it is the common base mode configuration. Another one, it's a CE, it's a common emitter configuration. And the last one, it's a CC, which is common collector configuration. This is not being asked, not in the syllabus, but we have derived the required relation for the common base as well as common collector. I hope this is clear. Is it clear? Is it? Great. So are you ready for the question? Are you ready for the question? Are you sure? Great. Let's begin then the journey. The question says that first keep your pen and paper ready and write up the data with me as well as start solving it. The current gain, beta, of a transistor is 50. The input resistance of the transistor, the input resistance of transistor when used in the common emitter, when used in the common emitter configuration is 1 kilo ohm. The peak value, the peak value of the collector AC current for an alternating peak input voltage, alternating peak input voltage 0.01 volt. Yes, this is the question. Let's see what they have provided. They have said that the current gain beta of a transistor is 50. That means beta is given, which is equals to 50. The input resistance of a transistor when used in the common emitter configuration, that means they have given it's a CE configuration, is 1 kilo ohm input resistance. It's an R inside R input, which is equals to 1 into 10 to the power 3 ohm. The peak value of the collector AC current, the peak value of the collector AC current, that means IC, is required for an alternating peak input voltage for an the peak value of the collector AC current for an alternating peak input voltage, that means V in is given, which is equals to 0.01 volt. Okay, great. So how will we do this? Look at this V in is given, R in is given, that means IB would be available. So what I understand is this is V in is equals to I input multiplied by R input. This V in, it's a 0.01. I input, we don't know. R input, it's a resistance, and that resistance is 1 into 10 to the power 3 ohm. So it's a I input, that should be is equals to 0.01, which is equals to 1 by 10 square divided by 1 by 10 to the power 3, which is equals to 1 divided by 10 to the power 5 ampere. This is called as I input as well as IB, because it's a CE configuration. Now what do you want? You want IC. So it's a beta is equals to IC by IB. So beta is given, and that is of 50 is equals to IC by IB. So IC is equals to 50 into 1 divided by 10 to the power 5. So this is equals to 5 into 10 divided by divide by 10 to the power 5. Let's multiply and divide it with 10. So this is 500 divided by 10 to the power 6, which is 500 microampere. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? No? Great. Ready for next question? Are you ready? Let's have a look. The next question. The question says that input signal to a common emitter amplifier, having a voltage gain of 1000 is given as V input is equals to 0.004 volt sine omega t plus pi by 2. the corresponding the corresponding voltage output signal. Yes, this is required. So what they have provided, they have provided V input, which is 0.004 sine omega t plus pi by 2. Next, they have given it's a common emitter amplifier. So when they said it's a common emitter amplifier, it's a CE configuration, and that we must understood that there is a phase difference between V out and V in would be there, and that phase difference between V out and V in, how much? Yes, how much? Tell me, what would be the phase difference between these two, between CE? Yes, there is a phase difference. There is a phase difference of pi by 2 or pi. What was it? What was it? Yes, pi by 2. So this is there is a phase difference between V out and V in would be there. And when I get V out, then that should be is equals to gain times V in. So gain, it's 1,000 multiplied by amplitude of this, it's a 0.004, it's a 4 divided by 1,000. So this has gone, and this will be the 4 volt. Now you can write down the relation on your own. I hope this is clear. Is it? Is it? Are you sure? Are you? Great. Ready for the next question? Let's have a look. The question says that the input resistance of a silicon transistor, the input resistance of a silicon transistor is 1 kilo ohm if base current is changed by 100 microampere. It causes the change in collector current. It causes the change in the collector current by 2 milliampere. This transistor is used as a CE common emitter amplifier with a load resistance of 5 kilo ohm. What is the AC voltage, AC voltage gain of amplifier? How will you do this? They said that the input resistance of a silicon transistor is 1 kilo ohm. It's an R input which is equals to 1 kilo ohm. And if base current, that is the delta IB, is changed by 100 microampere, it's 100 into 10 to the power minus of 6 ampere. It causes the change in collector current. It causes the change in collector current by 2 milliampere. That means delta IC, which will be equals to 2 into 10 to the power minus of 3 ampere. This transistor is used as a CE, common emitter amplifier, with a load resistance. It's an R out by 5 kilo ohm, which is 5 into 10 to the power 3 ohm. What is the AC voltage gain? That means voltage gain AV has been asked. How will we do this? So first, what voltage gain is? Voltage gain, it's a V output divided by V input. When I say V output, this simply I output multiplied by R output divided by I input multiplied by R input. This I output by I input, this is beta times of R output to the R input. When I say it's a beta times of R output to the R input, we don't have a beta. So first I will look forward to find out the beta. How will we do this? It's a delta IC divided by delta IB multiplied by R out divided by R in. Yes. So it's a voltage gain that is equals to delta IC by delta IB. This change, it's a 2 into 10 to the power minus of 3 divided by, it's a delta IB, which is equals to 100 into 10 to the power minus of 6 multiplied by R out. It's a 5 into 10 to the power 3. R in is equals to 1 into 10 to the power 3. So this has gone, this has gone. This is equals to 2 into 5 into 10 to the power minus of 3 into 10 to the power minus 6. It would be a plus 6 divided by 10 square. So this is simply 2 5s are 10 multiplied by 10 to the power 6 into 10 to the power minus of 3 into 10 to the power minus of 2. So it's a 6 plus 1 7 minus 5, it's a 2. It's a 10 to the power plus 2. This is the gain, and it does not have any units because it is the ratio of the similar quantities. I hope this is clear. Is it? Is it clear? Are you sure? Any doubts? Is there anything? Is there? No? Great. Next, let's look at this. The question says that a transistor has current amplification factor of 6060 in a CE amplifier. Input resistance is 1 kilo ohm and output voltage is, and the output voltage is 0.01 volt. The transconductance is a transconductance has been asked. How will you do this? So let's check what all has been given. A transistor has a current amplification factor of 60, and they have said it's a CE amplifier. That means beta has been given, which is of 60. Common emitter configuration has been given. Input resistance is given, that is of 1 kilo ohm, which we say is it's a 1 into 10 to the power 3 ohm. And output voltage is given, this is V out, which should be is equals to 0.01 volt. And the transconductance, generally what we call as a GM, that has been asked. How will you do this? What was the formula of the transconductance? This GM was V out divided by I in. Yes? Yes? No? Absolutely no. It was the I out divide by V in. Yes, now it's correct. So I out is IC. V in, it's an I in multiplied by R in. This is beta times of, beta divided by R in. Beta, it's a 60. This is 1 into 10 to the power 3. This is 10 to the power minus of 3 units. I hope this is clear. Is it? Is it clear? Are you sure? Any doubts? Is there anything? Is there anything? No? Great. Ready for next question? Let's have a look. The question says that in CE amplifier, the audio signal voltage, across across the collector is 3 volt. The resistance of collector, the resistance of collector is 3 kilo ohm. If current gain is 100 and base resistance is 2 kilo ohm, the voltage and power gain of the amplifier is yes, this is required. They have said that which amplifier? It's a CE, common emitter amplifier, has been given. This is given, common emitter, and CE amplifier, the audio signal voltage across the collector, that means V out is given, which is equals to 3 volt. The resistance of the collector, that means RC, is given, it's a 3 kilo ohm, it's a 3 into 10 to the power 3 ohm. And if current gain, that is the beta, which is equals to 100, and the base resistance, which is equals to RB, which is equals to 2 kilo ohm, which is 2 into 10 to the power 3 ohm. The voltage gain, it's an AV, and the power gain, this two are required. How will we do this? We have the relation of the AV, which is equals to the voltage gain. This is equals to beta times of R out by R in. Yes, so beta, it's 100 multiplied by R out. What is it? It's a RC, which is equals to 3 into 10 to the power 3 divided by R in, which is RB. It's a 2 into 10 to the power 3. So this has gone, and this is equals to 53, which is 150. This is AV, what we call as the voltage gain. Now it's a power gain, which is equals to beta square times of R out by R in. This is equals to 100 square multiplied by R out, which is equals to 3 into 10 to the power 3 divided by R in, which is equals to 2 into 10 to the power 3. So this has gone, this is 100 into 100 multiplied by 3 divided by 2. This is 5050. So this is equals to 5 3s are 15 multiplied by this and this. It's 10 to the power 3. So this is 15 into 10 to the power 3. It's a 15,000. I hope this is clear. Is it clear? Is it? Are you sure? Can it be done? Can it be? Correct. Ready for next question. You are doing quite good. Well done. Keep going. Let's work for the next question. The next question says that in an NPN transistor, the collector current is 10 milliampere if 90 percentage of the electrons emitted reach the collector, then the emitter current will be, yes, this is the requirement, that in an NPN transistor the collector current is 10 milliampere. That means they have given the IC, which is 10 into 10 to the power minus of 3 ampere, and they said if 90 percentage of the electrons emitted reach the collector, that means IC is equals to 90 by 100 of IE, and you want to find out the emitter current. So it's a very simple question. It's an IC which is equals to 90 by 100 into IE. This is equals to 10 into 10 to the power minus of 3 is equals to 90 by 100 into IE. So this IE is equals to 100 into 10, which is 1000, into 10 to the power minus of 3 divided by 90. So this has been gone. This has been gone. This is 10 to the power 3. This is 10 to the power minus of 3. This is 1 divided by 90 ampere. Yes, I hope you understand this. Now, if I have been asked to find out that the question is in the previous question, find out base current. So to find out the base current, I understand that IE is equals to IB plus IC, and now onwards I am having the IE. Sorry, IE. Yes, IE is available. It's a 1 by 90. Base current is required, and IC is given. It's a 10 into 10 to the power minus of 3. This is one of the approach. Solve this and get the IB. One other approach for this is, as they have mentioned that 90 percentage of the electrons emitted reach the collector. So if 90 percentage of electron reach the collector, it means the remaining 10 percentage of electrons is into the base. That means this IE is equals to, or IB is equals to, sorry, IB is equals to 10 percentage of IE, and you are having the I, and rest of the amount you can do it. I hope this is clear. Yes, both are the approach. You can go with any. Have you got this? Have you? Great. Now let's do the second category of question, which is based on the circuit diagrams, and we need to find out certain quantities. Let's have a look. The question is something like this. First, look at the circuit diagram. This is the transistor, and they have connected it with the resistance. It's a 2 kilo ohm. This is plus 10 volt, and here they are having one more resistance, which is of 245 kilo ohm, and now they have been connected with the base of the terminal, and this has been grounded. Yes, this is the situation, and the current is given, which is equals to 4040 microampere. Yes, the question says in the given amplifier circuit, beta is equals to 5050. Find VCE of transistor. So how will we do this? First thing you must understand is that it is having an arrow, and if it is having an arrow, this is emitter, this is base, this is collector. As emitter is grounded, that means this is CE, it's a common emitter configuration because this is grounded, and this will play a role on both the sides. So first thing, this is CE configuration. Next thing, what they want, VCE, that means they want the potential drop between this two. And as this will be on the output circuit, what I can do is that the total amount, it's a VCC is equals to VCE minus of ICRC. Yes, it's a VCE plus ICRC. This VCC, this is the supply voltage, and it is having two roles to play out. One of them it's the ICRC, and the another it's a VCE, voltage between collector and emitter terminal. And if it is having this role to play, VCE has been given, it's a 10. VCE, that is to be asked, IC, do I have it? No, but I am having the beta as well as I am having this base current. So what I can have, it's the IC is equals to beta times of IB. The beta, it's a 5050, and IB, it's a 40 into microampere. So this is equals to 5 fours are 20 into 0 into 0, it's a 2000 microampere. It's a 15 to 40. Yes, so this is 2000, which is equals to 2 into 10 to the power minus of 3 into RC. This is given, it's a 2 into 10 to the power plus 3. Yes, so this has given, this has given, this is equals to VCE plus 2 2s are 4, and this is 10. So VCE is equals to 10 minus of 4, which should be plus 6 volt. I hope this is clear. So basically this is the relation of KVL, and this is the question of KVL. It is not having anything, it is not having anything with the transistor. Yes, I hope you understand this. Okay, is it clear? Is it clear? Ready for one more question like this? Are you ready? Let's have a look to the next question. Let's suppose the circuit is something like this. This is grounded, and on this side it is the resistance of 4 kilo ohm, and this is plus 20 volt. This is the V input, this is 500 kilo ohm, and this is given, it's a 4 kilo ohm. Yes, so as the question says in the circuit diagram, in the circuit diagram, the input voltage, the input voltage is 20 volt VBE, and VCE is equals to 0. The values of IB, IC, and beta are given as So yes, these are the things that we required. This is the emitter terminal, this is the base terminal, this is the collector terminal. So these three terminals are there. It's an emitter, it's a base, and there is a collector. And we have been given that the input voltage is 20 volt. This is the 20 volt, this is V in. This VBE is 0, so the voltage between this two, it's a 0. This is VBE. This VCE is 0, so this is VCE, which is equals to 0. And the value of the IB, IC, and beta, the 3 R's required. How will we do this? What can be done? So what we understand is that this is 0, VBE and VCE. VBE is on the input side, so it's a V in, which should be equals to VBE plus it's an IB into RB. But as they have mentioned that this is 0, so this is 0 plus V in has been given, it's a 20. IB, that we don't know, multiplied by RB, which is equals to 500 kilo ohm. So this is IB, which is equals to 20 divided by 500 into 10 to the power minus of 3 ampere. This is IB. Now what about the IC? IC is on the output side, and when I say it's an on output side, this is equals to V output, or I should say VCC. It's a supply voltage, so the supply voltage should be is equals to VCE plus ICRC. But as they have mentioned, this is 0 plus IC, that we need to find out, multiplied by RC, which is equals to 4 into 10 to the power 3, and the VCC, that has been given as a 20. So this is IC, which is equals to 20 divided by 4 into 10 to the power 3. This is equals to 20 divided by 4, it's a 5 into 10 to the power minus of 3 ampere. I hope this is clear. So IC is available, IB is available, I can have the beta, which is equals to IC by IB. The IC, it's a 5 into 10 to the power minus of 3. IB, it's a 20 divided by 500, it's a multiplied by 500 into 10 to the power minus of 3. This has gone, and it's a 5 5s, that is 25 into 100 divided by 20, this is 5, it's 125. I hope this is clear. Is it clear? Is it? So can you do this kind of questions? Are you sure? Can it be done? Great. So let's look at these certain quick questions. The question says the relation between alpha and beta with current gain. So we are having the relation which says that IE is equals to IB plus IC. Now let's divide this. Let's divide this with IC. This is divided by IC. IE by IC. What is it? Yes, it's a 1 by alpha. This is equals to 1 by beta plus 1. So this is equals to 1 by alpha is equals to 1 plus beta divide by beta. I hope this is clear. Is it clear? Is it IE is equals to IB plus IC, and I have divided it with IC. Yes, so this is alpha, which is equals to beta upon 1 plus beta, and from this you can derive the value of the beta as well, that it is the 1 by beta is equals to 1 by alpha minus of 1. So it's a 1 minus alpha by alpha, but it is 1 by beta, so beta would be equals to alpha upon 1 minus alpha. So this is not correct answer, this is the correct answer. I hope this is clear. Yes. Look at the next question. The current gain alpha of a transistor is the ratio of, yes, alpha is the ratio of delta IC to the delta IE. This is correct. This is the beta. delta IC by delta IP. Next, okay, it is the next question. The current gain beta of a transistor is the ratio of delta IC to the delta IP. Next, in a transistor, the width of blank, yes, emitter region is slightly more than that of the collector region. Incorrect. Collector region is slightly more than the emitter region. Yes. Emitter and collector region are equal. No. Emitter and base region, not at all. So, is it clear? Is it? Now let's look at the second function of a transistor. I mean, it's a transistor as a switch. Let's have a look. When we say transistor as a switch can be analyzed by the behavior of the uh, base bias transistor and CE configuration as shown in the figure. You can see this is the common emitter configuration, and we have biased the transistors that this is the supply voltage, and that can be varied. This is the output voltage, and even that VCC could be varied, and we have applied it's a V naught. Yes, so we are going to measuring every voltages and every currents, and we will came to the conclusion. Let's look at this. So if we apply the Kirchhoff's voltage rule to the circuit, we can have this, that VBB, which is equals to IBRB plus VBE, and this VCE is equals to VCC minus of ICRC. So if we consider VBB as the DC input voltage, which we call as a VI, and the VCE as the DC output voltage, which we call as a V naught, then this V in would be equals to IBRB plus VBE, and V output will be equals to VCC minus of ICRC. So this is V output is equals to VCC minus of ICRC. If I plot this for the V naught versus VI, this is what we call as a transfer characteristic. So as long VI is low, basically this was the relation, that V output is equals to VCC minus of ICRC. So if VI is low and unable to forward bias the transistor, that means VC is high. Basically it is the situation when IC is 0, because IB is 0, because it is not forward bias. If IB is 0, that means IC is 0. If IC is 0, then this is V out, which is equals to VCC. So it's this region, and this region is known as the cutoff region. Next, if Vi is high enough to drive the transistor into saturation, that means IB, yes, in the second case, IB, it's a maximum. If IB is maximum, that means IC is maximum. And if IB is maximum, IC is maximum, that means V out will be the minimum. And when we say V out is minimum, this would be the situation that very minimum output voltage will be available, and this region is known as the saturation region. So if Vi is high enough to drive the transistor into saturation, then V naught is very low and it is very near to the 0. So when the transistor is not responding, it is said to be switch off, and when it is driven into saturation region, it is said to be switch on. So this shows that a very low input switches the transistor off, and a high input switch it is on. Or rather we can say that a low input to the transistor gives a high output, and a high input gives a low output. So the switching circuits are designed in such a way that the transistor does not remain in active states, and so that if it is not remaining in the active states, the transistor can be operated as a switch, because as a switch to operate, transistor must be operate in either cutoff region or saturation region. When we say that it is working on the saturation region, when we say it's a saturation region, this will behave as a on switch, and when we say it's a cutoff region, this will work as the off switch. Yes, and in the active region, yes, it works as the amplifier that we even discussed previously. This is the amplifier region. I hope this is clear. Is it? So ready for quick questions? Let's have a look. When transistor is not responding as a switch, it is said to be, yes, it is said to be switch off. Next, the blank input to the transistor gives a high output and high input gives a low output. Yes, the low input to the transistor gives a high output and high input gives a low output. This is the correct. I hope this is clear. Now let's work for the and let's look at the very unique feature of a transistor, and that is the transistor as an oscillator. So let's have a look what kind of work transistor can perform when it can work as an oscillator. So it is the function of an oscillator circuit is to produce an alternating voltage of desired frequency when only DC batteries are available, and the basic parts in the circuit are the an amplifier and an LC network. It's a inductor and capacitor network. So the principle of a transistor amplifier with positive feedback working as an oscillator, and let's understood that this will be the input, this will be the output, and here transistor amplifier will be there, and we are going to giving it back with the feedback. So that this is the situation with feedback amplifier. We will learn again what exactly or how feedback amplifier exactly work, but first look at this. So the amplifier section is there, which is just a transistor that is used in the common emitter mode, and the LC network, the capacitor and inductor network, consists of an inductor and capacitance, and this network resonates at a frequency that is 1 upon 2 pi under root of LC, and we keep the batteries are used to bias the transistor, and no external input signal is fed to the amplifying section. So this is how transistor can work as an oscillator. Now what feedback amplifier is, let's have a look, and how does it work. So when we discuss a feedback amplifier, we are talking about a two different kind of feedback amplifier. One is the positive feedback amplifier, and the another, it's a negative feedback amplifier. So we have two different kind of feedback amplifiers are there. One is the positive feedback amplifier and another is the negative feedback amplifier. Now what positive feedback amplifier is, that let's say this is the V in versus time, and this is the V feedback to the time, then even this will be in phase of it. This is the positive feedback. And what about the negative feedback, that this is, let's say, V in versus time, and this is the V feedback versus time, then this will be the out of phase. So this, if feedback is out of phase to the input signal, then this is what we call as the negative feedback amplifier. I hope this is clear. Is it clear? Is it? Are you sure? Now how does it work? Let's have a look. So basically this is the amplifier. The general situation is at from here we apply the V in, from here we get the output, and we know that V output is equals to let's say gain is the A, the gain of this amplifier is the A, multiplied by V in. This would be the situation that V out would be equals to A times of V in. But after a certain time, this gain start reducing, and you are not going to, or you are not having that much output that is essential. So what we are supposed to do is that we are arranging situations that this is the amplifier having the gain A, and this was the V in, this was the V out, and we are giving it back a certain segment. This is the beta segment has been given to the V input again. Now if this segment given to V in is in phase, then it is the positive feedback. And if now this has been given, if this has been given in the out of phase, then this is what we call as the negative feedback amplifier. Now do you understand what positive feedback and what negative feedback amplifier is? I hope you understand this. Yes. So we are not going to derivation of this, but I will give you the formula. So if A is the gain of, if A is the gain of the transistor CE amplifier, then gain with feedback is A dash is equals to V output divided by 1 plus, it's a V output is equals to V in, this is V output divided by V input plus beta times of V output. I hope this is clear. And this can also be written as A dash is equals to beta upon 1 minus beta into A. Yes, this A is the gain without feedback and this is the gain with feedback. I hope this is clear. So this is something like this. It's an A dash which is equals to beta upon 1 minus of beta into A. This is for positive feedback amplifier, and this is what we call as a Barkhausen criteria. It's a Barkhausen criteria, and it says that if beta into A is equals to 1, then this A dash it's an infinite, which means that you will get an output without having any input. I hope this is clear. Yes, and this is how it works as an oscillator. I hope this is clear. Is it clear? Great. So for positive feedback amplifier, for negative feedback amplifier, I'm sorry, for negative feedback amplifier, A dash is equals to beta times, it's a 1 plus beta into A. Please note this. Have you noted this? This is for negative feedback amplifier, and this the initial one which is equals to A dash is equals to beta upon 1 minus beta into A. This was for the positive feedback amplifier. I hope this is clear. Is it clear? Is it? Are you sure? Any doubts? Is there anything? Is there? No? Are you done with this? Are you? So, shall we do one of the questions based on this? Can I? Great. Let's work for the question. If amplifier, if gain of the amplifier without feedback is 10 and 10 percentage of output is again applied to 10 percentage of output is again applied to input, which is in phase, then find out gain with feedback. So they are talking about the, as they said that it is in phase. When they said it is in phase, that means they are talking about the positive feedback amplifier. It's a case of the positive feedback amplifier. The beta is given, it's a 10 percentage, that means it's a 10 by 100, and the gain of a transistor, gain of an amplifier is given, which is 10, and I have been asked to find out A dash. So this will be the situation. How will we do this? It's an A dash which is equals to beta times 1 minus beta into A. So this is equals to 10 by 100 divided by 1 minus, this is 10 by 100 into A is the 10. So this is equals to 10 by 100 divided by, it's at 100. So this is equals to 1 minus 1, and this has reached to the Barkhasan criteria. So if they have reached to the Barkhasan criteria, this would be the infinite. So now it has entered to the oscillatory session. Yes, that you do not need to provide any input, but it will work for you and it will provide you the output. I hope this is clear. Great. So now let's look at the quick questions. The question says, when a transistor works as an oscillator based on the principle of a transistor amplifier. Yes, the feedback is, it's a positive feedback amplifier, then this is possible. Next, the basic parts of a transistor when it functions as an oscillator are, yes, an amplifier and LC network. Yes, this both are required to work for the transistor as an oscillator. I hope this is clear. Great. So let's wind up the session over here. This was all about the transistors. Please revise it thoroughly, the part 1 and part 2 of the transistor, because this are the very high probability questions that is being asked in the examination. If you go through the previous year asked questions, you will find at least one question. If there are even chances, and many of the years they have asked 2 questions from this transistor. So this is very important. Please revise it. Please do as many questions as possible. Do every techniques of the questions that go with the theoretical question, as well the questions that are the based on the circuit diagrams. Please go through it. This will help us to get good numbers. Thank you. Have a good day. Take care. Bye.